Welcome for those of you that joined us for the VEI Contracting webinar series, the first of our fall series. Today we're looking at, the title of the talk is Developing Realistic Dewatering Designs using the Hydraulic Profiling Tool. I'm your host today, Bruce, and Farouk and Patrick will be presenting. What to expect today, I'll do a very short intro, probably less than 5 minutes, and then Pat and Farouk will take over, and they'll talk for up to 40 minutes, and we'll leave plenty of time for questions. If you do have questions, you can leave them in the chat or use the Q&A either way. Who am I? Who's VEI? Well, VEI, we were founded in 2003, so 22 years ago. We were formerly Vertex Environmental, but just made an acronym of our name. We specialize in environmental remediation contracting, in situ, ex situ, high resolution site characterization, and have since branched into treatment systems, water and vapor, and dewatering services. I'm Bruce Tunnicliffe. I'm founder and president of VEI, and I'm happy to be your host today. VEI has worked across the country, coast to coast. And we're very happy to say that we have done that. And we offer, as I said earlier, a host of services. Today, we'll be looking at the dewatering area of our expertise and sharing some information with you. We're also taking part in outreach, sharing this information. Speaking of outreach, I'll just share with you what is coming up. So today, we're looking at dewatering designs using the HPT. In a month from now, we'll take a look at closing LNAPL sites. You can read the title there. A month after that, PFAS remediation. That'll probably be a popular one. And closing out the fall series, we'll take a look at passive treatment barriers for metals and acid rock drainage. In other outreach or information to share, we'll be at the ONEA PFAS Summit that's coming up September 23rd. If you haven't signed up for that, it's probably a good one for you or your colleagues if you're interested in PFAS. And then the ever amazing REMTech conference is taking place mid-October, and we'll be presenting remediation case studies gone wrong at this one. And after that is RPIC in Ottawa. And so lots of learning and networking opportunities coming up. Also is smart remediation, which we organize, and we're establishing our Western Smart, so Smart Vancouver, January 20th, Smart Calgary, January 22nd, and then Toronto, January 29th, and Ottawa, February 12th. So if you're interested in learning, come on out to Smart Remediation. So today's talk is, well, I'll just pass it over in a moment here to Pat and Farouk. I just want to remind you, if you do have questions, if you can ask them in the chat or Q&A, and feel free to ask those questions anytime. We'll hold the questions until the end to let Pat and Farouk walk through their information. And then I'll read them or they'll read them, and we'll go through and answer all of your questions. So take it away, Pat and Farouk.
Thanks, Bruce. Thanks, guys, for showing up and coming to listen to us speak about dewatering designs and how the hydraulic profiling tool can help enhance those designs. So here's a quick agenda. We'll just go over briefly who VEI Contracting is, although Bruce has done most of that legwork for us, and who we are. We'll talk about some dewatering assessments and how those are designed. Those systems are designed. We'll briefly talk about some high resolution site characterization and then the HPT specifically and how that applies. And then we're going to run through a case study later on at the very end of this presentation to sort of guide everyone and to show how this tool is applicable with this application. Again, so here we are. VEI started out as a specialty remediation contractor, still remains that to this day, but we've also expanded into a variety of different contracting services. Farouk's a senior project manager here.
Yeah, senior project manager here. I come from a background in consulting and hydrogeological base, so I've done countless hours of dewatering assessments and spent endless hours in the field doing slug testing and different dewatering estimates that way as well.
And for myself, I have my master's degree from University of Waterloo, senior project manager here as well, and spent the majority of my time in consulting and also contracting here at VEI. So we're going to focus again, like we said, on the dewatering side of things and the high resolution site characterization, how we're marrying these two divisions and having one support the other.
Right, so let's kick it off. We'll set up a quick background, explain dewatering assessments and system design. So again, I'll elaborate on what dewatering assessments and system designs are, how construction dewatering volumes are estimated, and then what are some of the limitations or uncertainties of the current methods that exist today. So first off, dewatering assessments. Dewatering assessments, they're used to evaluate site conditions, determine dewatering methods, and ensure compliance with regulations. The goal is to establish a safe and dry, stable work environment during the construction activities. They aim to estimate the volume of water that's going to be removed, the duration that the dewatering would be needed, the cost sometimes, and then some potential environmental impacts if that's anticipated. Construction dewatering volumes, it's commonly referred to as Q, are determined through the completion of hydrogeological investigations. These consider hydraulic conductivity, K, the height, initial height or stable groundwater height to a lower confining layer if it's present, the height that the water table is going to be reduced down to, and then things like the radius of influence during pumping. I have some equations up on the right here. There's lots of different methods you can use to estimate Q. They're based on various ways. But the big takeaway here is you can see they rely pretty heavily on K, hydraulic conductivity, that drives Q. So the big takeaway from that is estimating K accurately is pretty important for the overall dewatering assessment and overall accuracy. To show you that, I have this little figure here that shows hydraulic conductivity on the X, and then the drawdown that you're trying to achieve on the Y. So if you look at the first one, the eductors, that's for relatively lower conductivity sites. These can achieve drawdown to various depths. That's when they're most applicable. As you move towards the right, you start to get more conductivity. So we're in the moderate zones. If you're looking at shallower dewatering targets, single well points or two-stage well points become more appropriate. If you're trying to achieve deeper drawdown, then we start looking at deep wells. If you go even higher than that, you're talking excessive amounts of water, then you have to look at methods to cut off flow through shoring or installation of cutoff walls or barriers. Again, the big point we're trying to take away from this is estimating K accurately is really important because it impacts your overall dewatering system design and what method you're going to take, what method you're going to apply for your sites. I have a couple figures here that just show different types of dewatering in the field. This is a two-stage well point system. They're benched here because the excavation is going fairly deep. But as you can see, pretty dry excavation. You can see access in the top right, so everything is stable and the construction can continue. Another example here is probably more common, or when people run into more, is road reconstruction. Again, it's a well point system, but it's a linear infrastructure. So these can be turned on and they move forward as the project continues. I've also included an image of a water treatment system. And what I want to really highlight here is everyone thinks about the dewatering aspect when they're estimating Q, but they don't think about any treatment if there's impacts, for example, total suspended solids. You've got this Q, the dewatering rate, but you don't think about the impacts from the treatment perspective. That flow rate, a system needs to be designed on the other end of it that can satisfy that flow rate and treat the contaminants of concern prior to discharge. So Q doesn't just end with getting the water out of the hole, it then takes it to the discharge to the environment or to a sewer. So let's talk about the different methods that exist for estimating hydraulic conductivity, their advantages and some potential limitations. The first one is grain size analysis. Advantage is it's quick and relatively inexpensive. You're just grabbing grain size from a borehole. It's lab-based, and it's useful for an initial estimate to give you kind of an indication of what you're dealing with. Some of the limitations is its accuracy and applicability are limited. And I say that because usually it's good for sands, but as you approach silts or clays, it's really kind of a guess off the D10, D50, and those aspects. The next common one is single well response test. It's commonly referred to as slug testing. This is relatively quick and cost effective. You send out one tech with some data loggers, minimal equipment. You're just running this test on multiple wells. Limitation here is the area of influence, or the area that you're assessing, is pretty limited. You're kind of limited to that single well. You're checking the response of that single well. And there are accuracy concerns in the sense that you're relying on the well being constructed properly and being screened in appropriate locations. There's human error brought in. You have to bring this data back and analyze it and make judgment calls. So there are some accuracy concerns there. Finally, there's pumping tests. This is probably the best methods that we have to date. Pumping tests have a large area of influence. You're pumping from one and monitoring adjacent wells to establish impact on the aquifer. It's a pretty comprehensive test. You get good data from it, and you can evaluate in situ conditions. The limitation for it is it's somewhat time consuming and it can be expensive because you usually have to install 1 or 2 pumping wells to carry out this test. There's a lot of upfront planning from that drilling and then the data logger placement and data management. And if you're dealing with an impacted site, you sometimes have to think of disposal concerns because these generate water. So summary of these methods, they typically rely on a limited number of monitoring wells that are installed as part of a hydro-G or geotech or ESA investigation. These wells are screened within discrete screen intervals, and the aim is to provide representative estimates of groundwater flow across usually heterogeneous geologies. It's not like it's just one sand type or one clay type, right? We usually run into various geologies, especially in Ontario. A typical construction dewatering site, the planning for it relies on data points that are pulled from 10 wells. So they'll look at the up to 10 wells that they have on site, and they'll look at the water levels and evaluate the geology that way. Of those wells, typically it's 2 to 4 of those wells that will be correctly installed, developed, tested, and analyzed as part of their analysis. We're humans here, we make errors. You can't avoid that aspect of it. But data collection, human error from data collection, data processing, it can result in inaccurate estimates of K, and that in turn impacts the dewatering flow rates in the sense that it boils down to additional project costs or variability in project costs and/or delays or changes in timelines when you think about approvals in the implementation. The idea here is time is money and money is time. These numbers matter. So gets you thinking, is there a way to increase data resolution and reliability when estimating K? Is there a way to kind of minimize the human error? Is there a way to get more certainty in the numbers we're collecting from in situ? The obvious answer in today's day and age is, of course, it's AI. We got to use AI for everything. I'm just kidding. Relax. I promise. This is all using tools that exist, and it's all data crunching. No ChatGPT needed to do what we're talking about. I'm going to hand it over to Pat here to talk a little bit more about the high-res tools and HPT, introducing it.
Perfect, thanks. Maybe AI will be part of high-res characterization in the future, but for now it's not. It's all human and machines, the dumb people and the dumb machines. So what are high-res tools? We're going to talk about the HPT in depth and maybe look at some advantages that the HPT might have over conventional methods of estimating hydraulic conductivity. So the US EPA defines high-resolution site characterizations as strategies and techniques to scale appropriate measurement and sample density to define contaminant distributions and physical context in which they reside with greater certainty, supporting faster and more effective site cleanup. That's a mouthful, and that's mainly towards the site contaminant side of high-resolution site characterization. But the other part of that is the HPT, and we're looking at different scale-appropriate subsurface permeability distributions and how they are, make up the boreholes and how they are transcribed within there. So other high-res tools, which we'll just touch on so you understand what they are, is the laser-induced fluorescence that looks at free-phase products, the membrane interface probe, and the low-level membrane interface probe. They look at dissolved phase and anything stuck in the soil from a contaminant distribution standpoint. And the hydraulic profiling tool, that's the star of our presentation here, looking at subsurface permeabilities. The nice thing is, if you do have a contaminated site and you do want to look at both contaminant distribution and subsurface permeabilities. These two tools are now combined all into one here in-house. And if you ask really nicely, maybe we can combine the LIF tool with the HPT tool down the road as well, and we can get a whole host of data in the future on a single push. So what does the laser-induced fluorescence look like? Just so everyone can see what it looks like. You have everything on the depth on the y-axis and our response signal on the x-axis. The larger the response signal, the more the contaminants are glowing in the ground. And with the LIF tool, we have this neat ability to be able to almost fingerprint the contaminants that we're looking at, so we can kind of identify what we're looking at as well. And you see how they're distributed within the subsurface. So this first log in green, that looks more like a diesel or heating oil spill. The one on the right is a kerosene or a jet fuel or high octane gasoline type of product over there on the right. Now, similarly with the MIP tool, again, depth is on the y-axis, and our different detectors, here we have multiple detectors, whereas the LIF is just sort of one detector, are all responding on the x-axis. And with the PID and the XSD, which is a halogen-specific detector, when these two are mirroring each other, we're getting a good correlation for something that's chlorinated solvents. Over on the log on the right, when the PID and the FID are responding with each other, that's good indication that we have hydrocarbons in the ground. So that's just some backup information. So if you're ever interested in contaminant distribution, this is how these tools display the data. And we'll actually see something similar with the HPT. So how does the HPT work? Like, how does it actually gather this data? So what we're doing is we're taking clean water uphole and we're moving it through a pump and down a trunk line through a preset strung drill rods. And we're measuring that flow of water that comes out of that HPT injection port with a downhole pressure transducer. We're measuring the back pressure of that on the with the downhole pressure transducer so that we can profile that with the depth. Then additionally, you'll see an electrical conductivity probe at the bottom of this tool, and that's actually profiling the soil type. The coarser grain materials are going to have a lower EC reading, whereas the finer grain materials are going to have a higher EC reading. So we can get a sense as to what type of geology we're in, and we can confirm that with the HPT pressures that we're seeing as well. All of this to say is this is a real-time data assessment for the formation and the geology, and also as well as the permeability on a per centimeter scale as we're profiling down in real time. We get this information and the technicians can see it in real time. They can take a picture and email it to the project manager saying, this is what's happening right now. This is the data we're gathering right now. And then on the back end of that, the software will actually estimate your hydraulic conductivity for your saturated zone using an empirical formula, and we'll go through a little bit of that later. So just as we saw with the LIF tool and the MIP tool, we're seeing the similar type of graph, similar set of data. We have our EC readings on the first set of data. That, like I said before, the higher the EC reading, the finer the grain material. So in this particular log, we have fine grain materials moving into coarse grain materials at about, transitioning from 5 down to 7.5, and now we have this nice sandy aquifer down here. And in the middle, we have our HPT back pressure. That's this purple line. And you'll see when we're in those finer grain materials, we have higher back pressure. That makes sense. You're not going to be able to move water through silts and clays as easily as you will through sands. And on the last graph, we have the estimated conductivity, and that's done on the back end. So again, continuous real-time measurements and a constant push. The only time we really stop to push is to put a new rod on, and then we just keep trucking along, going down in the ground. And as I said, as I mentioned before, we have that increasing clay content up the surface for this particular log, and then down below we have this nice sandy aquifer down below. So intuitively, the higher back pressure, you have lower permeability. The lower the back pressure, you have higher permeability. Think of it this way: the higher your back pressure is, you're probably in some sort of tight material like a clay. The lower the back pressure, you're in something nice like a sandy gravel. And I'll mention the K values are what's back calculated at the end of everything, and conductivity is calculated or estimated using not only this pressure profile here, but also the flow that is captured with the HPT as well. So how did they do it? Well, Geoprobe did some extensive studies down in the States when they were designing and making this tool. It uses a combination of pressures and flows from the HPT tool to then back calculate and estimate what our K values could be within that formation. And it does that with each interval that we're capturing data. This is the empirical formula they've developed with their HPT tool. It's been proven to work quite well on multiple sites across the world. I know the HPT is deployed globally. So how does that actually work? How do you actually get that how do you get that hydraulic conductivity? What we do is a dissipation test, and that's this little triangle right here in the middle of this log you'll see here. This line is actually the absolute piezometric pressure line. And so the water table is spotted here at just over 2 meters. And the dissipation test is how we get this water table identification. We shut off the flow of water at surface, and we were able to then measure how quickly does that water within the trunk line of that HPT tool come down and equilibrate with the formation pressure. Once that's done, we're able to then spot the water table. We say this is where our piezometric pressure is, and the software does the rest, calculates the estimated K and our water table depth. So is it easy? It can be. The downhole pressure is recorded with that dissipation test until we get that equilibrium with the formation pressure, but it should be completed in a nice sandy or coarse grained material, just for not only efficiency, but so that we're able to get that absolute piezometric pressure to equilibrate with the formation pressure. If it's not allowed to fully dissipate, which you can see here on these first 2 data points, these are all from within the same log provided from Geoprobe. The first 2 were shut off prematurely, and they were not allowed to fully dissipate. They just show what happens within this the graph. The last 4 here were able to get a full dissipation within that water column, within that HPT location. And you can see how with depth, there's a linear trend within that absolute piezometric pressure or static pressure. Think of it this way: if you're diving into a pool or any kind of body of water, the amount of pressure that you feel on your head or your body is linear with depth. The deeper you go, the more pressure you'll feel, and it's a linear relationship, and that's what you're seeing here. And without getting that dissipation test correct, not only will your water table depth be off, but your hydraulic conductivity estimate will be greatly affected and will not be reflective of what's actually in the formation.
Okay, so this is where I started to look at this data during a dissipation test, and I'm wondering if any eagle-eyed attendees today have noticed that these dissipation tests strongly resemble the traditional falling head slug test that the ministry requires as part of your dewatering assessments. This kind of clicked for me. Just to remind everyone, you can estimate hydraulic conductivity through the pressures of HPT through that empirical formula that Pat was talking about. But this had me thinking, well, I have all this data here. Is there a way to estimate hydraulic conductivity using the data from the dissipation testing instead of that empirical formula, or to supplement that empirical formula? So this is where we brought in the HPT tool and we said, okay, let's do some testing. Let's try to figure this out. What we want to do is compare how do the K estimates that the HPT provides through the dissipation test compare against K estimates that are determined through the conventional or traditional slug testing methods. So the first step is we have to find a site that had homogeneous sand or subsurface geology. It was continuous, that was controlled. It kind of fit all those assumptions that you're taught in university about continuous aquifer that goes forever and sand in every direction and so on. So we actually did find this site. Then we had to get independent slug testing carried out on the well. We're going to call it MWX. We did this. We had a consultant carry it out independently of us. They didn't share any of their results with us until afterwards. Then we advanced an HPT point into or adjacent to MWX, and we carried out multiple dissipation tests. We used the results and analysis from the dissipation test to estimate K using Horslav's method. And then we compared those to the overall accuracy from the slug tests that were previously conducted by the independent consultant.
Okay. So I'm going to walk you through the log and how it compares to the traditional borehole. So first thing to note is the borehole was advanced on site prior to any kind of active construction. When we got on site, this was an active construction site. So there, the top 3-ish meters were already filled in. So there's extra depth on ours. So we had to line everything up to make sure it was correct. Now you'll notice that our water table was just around 5 meters, and when we account for the elevation change, we were actually pretty close to where they measured water in the groundwater monitoring well adjacent, MWX. Very good agreement when you consider all the seasonal fluctuations that could happen, especially in a sand. The next thing we noticed was we had a nice compact layer of sand in the borehole log, and when we line this up against the HPT log, we can actually see that layer of compact sand with this pressure log slightly increasing. And then you'll also notice on the EC side of things, we have a couple of spikes on the EC, which could indicate actually maybe some very minor finer grained materials in there that could also look like compact sand or a more compact version of sand, especially if they're not very thick or visible. You would still get that in the field from the visuals. And you also see over here the hydraulic conductivity dips in that compact sand layer, which makes sense if you think about it. It's more tightly packed, it's more tightly together. Your hydraulic conductivity is going to dip in that area. And you see everything rebound when we get back into that loose sand, again on the HPT as well. All sort of 3 streams of data here would correlate to that loose sand coming into on the borehole log.
Okay, let's talk about the data. So we took that dissipation test I was talking about earlier. This is just standard for any kind of slug test data you do. We turned that into a water level figure, and we then took the next natural step is to normalize that data to look at the quality of data. We then applied Horslav's method and gave us a 2 × 10⁻⁴ meters per second conductivity. And then we compared that against the consultant's independently determined slug testing K, and results were pretty similar. Honestly, you can tell 2 × 10⁻⁴. There's some minor variation there, but that's standard within any slug test. Remember, we're talking orders of magnitude. We also took advantage of the results to compare them against the hydraulic conductivity estimated using that empirical formula. So that's that blue line that you're seeing on the third or on the far right. And yeah, once again, 2.2 × 10⁻⁴. So 3 independent methods that all produced very similar results kind of gave us confidence. Okay, HPT has potential here to produce accurate results. Can this be applied in other situations? Before we go into that, I'm just going to highlight some, or I guess Pat will highlight some advantages here of the HPT.
Yeah. So you're collecting real-time soil permeability and electrical conductivity data. And when I mean real-time, as fast as the probe is advanced, data is coming up into the laptop and you can see it being drawn on the logs. This allows for an adaptive field program where you might have something unexpected in the subsurface happen. You might find a highly conductive seam. You might find this massive clay layer where nothing's being permeated and nothing can get through. And instead of just sort of going by what the plan says on the sheet to say, we have to do these 5 locations and these 5, they're immovable objects, you can actually develop a program to be more adaptive and flexible and say, hey, this is interesting. This feature over here is very interesting. We need to chase this. We need to understand this better and delineate it better. All can be done, not only in the same day, but over multiple days in case you have that luxury. And it allows for a high number of locations to be done in one day. The depth that you have to reach really will depend on how, and access will depend on how many you can get done in a day. Typically, if we're doing maybe 20-foot locations, 25-foot locations, you can probably count on 5, 6 of these done at a day, maybe even more, depending on how well site access is for that particular location. And then, like what Farouk had indicated, you carry out in situ falling head or slug testing with these dissipation tests within it, and it avoids any kind of well interference or well construction issues that might have happened, because you're measuring in situ. The probe is measuring directly within the formation that's contacting the probe. So there's no sand pack in the interfering with it. There's nothing to bias it up or down. It is what it is. So here's just a quick representation, and there's a 3D representation of somewhat the data looks like in a fence plot. But if you look at a single well response test, and we're using the data that we just collected at MWX and our HPT location, the single well response test, that's 1 point of data. The falling head dissipation test is 1 point of data. Using that, the entire estimated K, you're looking at 300 points of data to confirm that that average hydraulic conductivity across that depth interval.
Okay, so to recap here, we tried HPT. We've kind of proven that it has the potential to produce accurate results in a sand condition. We wanted to take this to an actual real site here and look at variable geology and look at the results we get. So I'm going to talk about a case study for future development. I'm going to give a summary of site details, a comparison of the slug testing data and the HPT data, and then some on-site applications, the HPT, after we got this data, and some takeaways from it all. So the site we had is a future development comprised of a multi-story high-rises and an underground parking facility. The proposed underground parking facility extends approximately 10 meters below ground surface. The geology of the site is fill and sand underlain by an undulating silt till layer. So there's variable depths of the silt that appear. A dewatering assessment was completed by an independent on-file consultant before we were involved. They had completed slug testing on 3 out of the 5 wells. They estimated K to be approximately 6.43 times 10 to the minus 5 meters per second. And that translated to an estimated Q of 6.5 million liters per day, or 1,200 gallons per minute. The client brought us in requesting some supplemental details on the subsurface permeability and the geology. They wanted us to support them with their dewatering system design and shoring design, because we're talking about quite a lot of water. And once you get to that level and that depth, we're talking about a lot of money. VEI proposed a 2-day HPT program. We wanted to confirm the subsurface geology and the K values adjacent to the existing monitoring wells that were slug tested. And then we also want to collect some supplemental data within areas outside of the dewatering assessment's initial scope, so address some data gaps as well. To do that, the investigation included the advancement of 5 HPT wells directly adjacent to the existing 5 wells that were installed, as well as advancement of 7 HPT points in other locations of interest throughout the site.
So we're going to look at one data here, or one of the HPT points that's co-located with one of the other monitoring wells that had the hydraulic conductivity slug testing completed. Now, without going into too much detail with all the data and what it means, we have our water table spotted with the HPT here just beyond almost at 2.4 meters. Again, agrees pretty closely with the monitoring well data as well. Remember that there's going to be seasonal fluctuations. This is what the water table is on this day at this point. I don't know if this was collected at the same time of year and whether there was a drought or if there was a wet season just before that. Then we have a sand layer that we're picking up here on the HPT, and we're looking at if we look above the sand, we're looking at fill essentially here from surface down to just under 3 meters. And we're seeing some variability within our EC, and that would be looking at like maybe there's a silt layer in here, or there's a very thin clay lens or something like that. And if you're looking at the description in the borehole log, you're going to see traces of sandy silt, some here and there. And then you're also going to get sand and gravel coming in the fill as well. And that is going to show up when we get those dips or those valleys within the EC. And then we picked up sand, just after 3 meters, and sand starts to show up in the borehole log in earnest, almost at 4 meters. But if you're looking at this description here, sand and gravel is actually showing up just before that. And sand and gravel is coming up within this fill as well. So, sand is relatively, it's within this fill layer as well, but it's only just a clean sand after just around 4 meters. Okay. And then we'll just also note the silt and sand transition zone down here. They picked up that zone right around 7.5 meters. We're picking that up just a little bit more shallower than that. And again, that just could be variability of where we're spacing, where the monitoring well is, where we are. And then there's also variability within, what is the technician seeing versus what are they pulling out of the cores versus what is the HPT seeing. And we're seeing this silt and sand transition zone especially come in when we get that high spike rise in that HPT permeability. You do see a little bit on the EC here, but it's most present here when you get the permeability rise. And you'll see the conductivity dive when the pressure increases. So again, we felt that we had very good correlation between what the borehole logs were saying and what the HPT data was saying as well. They're both speaking the same language.
Okay, so let's get into the data. And bear with me here. It's going to be a lot of data we're going to throw at you. I'm going to try to walk you through it. Don't worry, we have this webinar available online. At the end of this, we're going to share it with everyone. You can review this and you can reach out if you have any questions afterwards. Just try to focus on the general message I'm conveying about the results. So look at the 3 wells we have and the slug tests that were completed independently by an on-file consultant. Note that that's 1 data point per K, 1 data point for the screen that they're testing in 1 slug test. The ranges are from 10 to the minus 5, 10 to the minus 6. Then we look at the HPT dissipation testing so that was our version of the falling head test using the HPT dissipation testing. Those are typically, or what they turn out to be, is 10 to the minus 4, so slightly higher than the K slug testing results by an order of magnitude of 1 or 2 orders of magnitude. We then took an average of the K that was determined using the empirical HPT formula. This average was over the screen length. These screens are 1.5 meters, so 150 data points averaged to create the K. Again, these are 10 to the minus 4, 10 to the minus 5. So generally matching the HPT results for the dissipation testing. And then we also took an average using the empirical K across the entire identified sand unit. So reminder that the silt layer is undulating, so the thickness of the sand layer varies at different locations in the site. Hence, we have different amounts of data points that we're averaging across. So quick comparison of these results and what do they show. Generally, there's good agreement within the HPT results from the dissipation test versus the empirical formulas. Reminder, these are all independent tests, with the exception of HPT 15. That one showed a order of magnitude higher than the empirical formula results. That I was wondering what's going on here. Why is this one different than all the others? So we actually, because we have this real-time data and we have these logs, we looked at where the dissipation test was done. It was actually completed in a higher conductivity zone than the other areas. You can see it right there with that triangle. There's about 1 meter of high conductive sand in that zone. So we're able to understand that, okay, that was just subject to that geology in that specific location, and explains why it's slightly higher. It's not, I wouldn't call it an outlier. It's just, remember that we're talking about an average across a screen length or a sand unit length versus 1 discrete data point. In terms of when we look at the location MW101 versus HPT 15, there's generally good agreement with the results. They're all times 10 to the minus 5. So it gives us confidence, again, the HPT can match slug testing results. When we look at the other data points, there's good agreement between the HPT points, but they seem to be an order of magnitude higher, or 2 orders of magnitude higher, which could be an indication that there's actually just more conductive in those areas than the slug testing originally identified.
So we like to take our data and play with it and try to visualize it in 3 dimensions so that everybody can get a really good sense of what's going on and really explain what's happening in the subsurface. So here we just mapped out all of our HPT data and all of our estimated K data in meters per second and came up with a bunch of fence plots. Now this fence goes north to south, and then we start building upon this, and we have more fence plots that are going north to south. And you can see as these fence plots, as you go west to east across the site, and these north-south fence plots, you can see the initial fence plot over here on the west does not have as conductive of a zones, or it's not picking them up as much. That by the time you get to the center of that site, you're getting to I'll annotate this laser pointer. Here we go. At this middle point, this middle fence plot, you're getting a lot more of a conductive zone, and then you're seeing a similar conductive zone over here on the eastern edge of the site. So then if we look at the orthogonal view of that, now we're going east-west and across the site, you'll see a similar trend. We're getting that lower conductive zone on the western end, and then it's getting more and more conductive as we move east on the site. And then this is just everything sort of put together, and you're looking at a bunch of fence plots that really indicate that we have a lower conductive zone over on the western side, and then it pinches out and we get this really high conductive sandy aquifer here over on the eastern half of the site. So what is the results from this? We have that, like I said, we have that higher conductive zone on the eastern half of the site, a highly conductive zone between 4 and 6 meters thick sand layer. In terms of meters above sea level, you're going between 318 and 314 meters above sea level. I'll get to why that's important in a minute. The proposed development had extended its underground parking down to 315 meters below sea level, and that is going to indicate to us, based on that hydraulic conductivity, you're going to need extensive dewatering based on that quick analysis. So those lower conductivity units on the western end, maybe you're not going to need that much dewatering over there because the natural geology will help combat that. And those protruded down to about 313 meters below sea level. So you're going to have probably some shoring down there or cut-off wall once you get down that deep, just to help combat the silt layer below the silt layer. So what does that all mean? If we remember to the initial thought of this presentation, getting your hydraulic conductivity right really helps bring clarity as to how much estimated dewatering or Q you're gonna have on the site. So we did a sensitivity analysis, and if we went with the slug testing that was conducted by the consultant, we have 6.43 times 10 to the negative 5, and that yielded, like we said before, about 6.5 million liters per day. If by some strange reason, maybe the hydraulic conductivity is closer times 10 to the negative 4, you're going to be up 2 million liters per day more water coming into your excavation that you're going to need to account for in dewatering. I don't need to tell or emphasize that that's huge, and that's not a huge change. It's a half an order of magnitude when you actually look at the numbers between your K values. That's not a lot of margin for error when you're talking about 2 million liters per day. So what happened? So between the client and the consultant and VEI, we all sat down and we reviewed the results from everything. They did a quick cost analysis weighing the probable dewatering costs with the increased shoring and to get that extra deeper underground parking that was originally proposed. The results indicated that removing one less parking level would likely reduce construction costs in the long run. And so they decided, you know what, it's probably just best that we just don't have that extra underground parking layer. And that was all based on informed, data-driven designs. So thorough understanding of your subsurface geology and estimating your hydraulic conductivity is essential when you're looking at construction dewatering estimates and making sure you pick the right system. If you remember back to in the beginning, different depths, different drawdowns, different hydraulic conductivities require different dewatering systems. Each of them have different associated costs with them. So you want to make sure you get all of those things right. If you're using, low resolution in air quotes, slug testing only, you may not capture all the heterogeneity that you might see on the soils of the site that the HPT might be able to pick up for you in real time. So those inaccuracies in K estimation, like we just saw, can have a significant impact on your over or underestimation of your Q volumes that you're going to be getting with dewatering. So incorrect, it also could point you in the incorrect selection of your dewatering approach, over or under designing of your dewatering system. And that ultimately will delay your project timeline because you're going to have to re-permit or redesign the system and rescope everything. That's all to say these are extra costs to the projects that could have been avoided in the first place. So when looking at dewatering and looking at those overburdened sites, the HPT can be used to supplement those dewatering assessments and help optimize your dewatering or shoring designs to help prevent any of those extra delays, those extra overruns and costs. None of those seem to be welcomed by any client. Thank you for everyone for your for listening to us yammer on here for a while. We'll be happy to take any of your questions.
Yeah, thanks, Pat. Knowing that there's, you can hear them clapping, but here you go.
Yeah, I see a standing ovation, really.
Great. Yeah, thank you both. No, that was good. It's a complex topic and innovative as well. You guys presented it well. I've got a few questions here. One from the audience here. Actually, I should say if anyone has any questions, feel free to chime in. We will answer questions for the next 12 or 13 minutes. And if there's no questions, then we will end early. But feel free to ask any questions in the chat or in the Q&A. One of the questions was asked early on, and this may be something that you've covered, but maybe you're going to expand on it, Pat and/or Farouk. Can the dissipation tests for the HPT be conducted in fine-grained deposits and tills, or are they only really accurate in coarse grain? Maybe you can comment on that. How accurate do you believe they would be in different soil types?
It's a good question. Technically, yes, they can be completed in those really tight materials. I wouldn't do it just because it would take forever for those things to dissipate. You could be looking at hours or days, really. The operators were trained to look for those sand seams, those really highly conductive zones below the water table to conduct your dissipation tests just for an efficiency standpoint so that we can get that data, capture that data, and move on. So they can be completed in those fine grain materials. I don't recommend it, and I only would recommend those coarser grain materials to be completed dissipation tests.
Yeah, let me approach it from a different perspective from the dewatering perspective. If I'm doing a test in a tight material like a silt or a till, it's going to take a long time. I already know that there's not going to be a significant amount of water being produced from a dewatering perspective, right? I'd rather go chase the sand seams that are going to make trouble for me when I get to the dewatering stage. You're better off if you identify that silt till layer. You have the geoprobe on site, put a well, hang a data logger, and come back in a couple of days and get the data you need that way.
Yeah.
Okay. Thanks. We have a few more questions coming in. I'll just ask it out loud, I guess, in no particular order here. What is the cost has come up? So probably an expected question.
I have a bingo card of when cost would appear.
Yeah, cost.
It's going well for me here.
So what is the cost and timing between a slug test and an HPT test? So maybe compare that. Do you have a rough idea of the difference in total cost between slug and total cost for HPT?
Well, so HPT, you're going to have the equipment. You'll see on the slide here in front of us. This is the picture of the actual equipment on site. So you'll have an operator, you'll have the equipment on site, you'll also have a geoprobe on site and like a geoprobe operator. So there's a, like a significant investment in cost to do HPT. It's a little unfair to say what's the cost of one HPT like dissipation test versus one slug test, because you're comparing apples and oranges in a way. If you're going to be doing an one HPT test, you're actually going to probably be out there for an entire day. The cost of that, probably about $6,000 a day, plus or minus mob and overnights and stuff like that. But you're looking at having all of that equipment on site and all the labor on site to do so. And you're going to need to do locates because you're drilling. To do a slug test, you need a technician and a data logger or two, and the other equipment that you would need to do a slug test. It's been so long, I don't even remember.
Well, yeah, I want to comment on that because I want to make sure we're talking apples to apples. If you're talking about doing hydraulic connectivity assessment through slug tests, you still need to drill the wells. So that rig is still going to come on site.
Yep.
And then you need to go develop the wells. And then you need to actually do the slug test. And then you need to go analyze the data. And then you get your number, right? So when I think of that cost compared to our approach, which gives you a real-time analysis on the site, you can do, depends on the geology, but I mean, we did how many? 12 points in 2 days?
15, I think.
And we stopped because we were done.
Yeah, we just ran out of space. We ran out of things to do.
Yeah, so like keep these, it's a hard apples to apples comparison. I would recommend in a perfect world, do the HPT first, find your conductive seams throughout the site, and then install your wells because the geoprobe's on site already. So install your wells, and then you're testing the most important points of interest for the site.
Yeah.
Think of it as a supplemental addition to your investigation.
Yeah, it's not necessarily here to replace slug testing or to replace that.
It's not yet. We'll see how the dissipation data grows over time.
Yeah.
It also says it might appear, maybe you can comment on it, that the HPT provides more accurate assessment of the K value, perhaps with more information per vertical meter. But as such, do you think that the factor of safety usually applied in dewatering could be reduced? Like in the overall picture, could you use it and then perhaps have a lower cost estimate when you go into a job?
Yeah, and that's why I brought in the idea of system design, not just the estimating Q, because it doesn't end with just getting the Q. You have to build a system that can handle those flow rates, right? So it matters. And the typical way the dewatering assessment's done is they'll build in so much factor of safety. You'll build in highest water table, your thickest sand aquifer, your maximum drawdown. You get your K, your highest K that you've observed on the site. You do that, you estimate Q, and then you'll apply a factor of safety of 2, 3, 4 on top of that number when you estimate Q. So you're building in so much redundancy in the Q. When it comes to us as contractors, I get a number that says it's 2 million liters a day, for example. So I build a system that can do up to 2 million liters a day. Well, then when we get to site and we strip away all those factors of safety, I have a system that's actually running at 500,000 liters a day. So a quarter of that flow, but I built a system that's 3 times the cost for the client. So it's something to keep in mind why it's important to get accurate values.
Mm-hmm.
Another one too, this one. So has the data collected and dewatering rates estimated by the studies that you showed here been compared to actual dewatering rates?
Not yet. That's the next stage. I got to keep in mind
we're still working on it.
This is very new. We have the sites. We're just waiting for them to kind of clear their plans, and maybe there'll be a follow-up webinar with an update on it. To that point too, if you have sites you think that this could benefit you, or you have sites that you think are going to go to dewatering soon, we're always looking for more data. We're always looking to work with consultants and clients to build this case up and prove the concept even further. So please don't hesitate to reach out to us about it.
Multiple lines of evidence is a really a good way of gathering all of this information, presenting a very well-rounded case to say we only need a system that's designed for this because we have all of this evidence to say that's all we need. And ultimately, hopefully, that at the end of the day, that saves everybody headaches either from over designing or under designing your system at the end of the day. So we just need more data points.
And then another, we have only we have 5 minutes left for a few more questions for those interested. Is it says in relation to a project timeline for a development site, when is the best time to complete HPT?
Take this? You want?
I'd say from a calendar's perspective, not in the wintertime, but from a project timeline, whenever you're doing your hydro-G assessment, we're not like the HPT is not going to be there to replace that hydro-G assessment. It's there to supplement it. So whenever you're doing that process, for sure, get us involved at that point. If you've already gone through your hydro-G assessment and you maybe have questions or you might have data gaps, this is also a good application to fill in those data gaps and confirm what you're seeing on the hydro-G across the site. Like I said, like we pointed out before, a lot of your hydro-Gs are done on a couple of wells, a couple of points of data across and applied across the entire site. But especially in Ontario, you can get areas where you have very high heterogeneity across the site. In our site that we just looked at, it's not a massive site, and we've got major differences in the sand unit and where those silt layers are, and that really affects your overall dewatering plan. And for a very small amount of time, you can get that data in as quick as possible. So if you have done your hydro-G assessment and you haven't done construction yet, and you want to fill in those data gaps, you still got time to do it. Like it's still.
I'd say there's two peak moments. One before you drill anything.
Yep.
Let us help you address where to put these wells and how to, maximize the return on your wells. Or if you've already done the site and you're finding data gaps or uncertainties, that's another opportunity. So you get two big chances to do it.
Okay. And there's another question here. Has there been any regulatory communication regarding the approach? I'm not exactly sure what the question is there, but
Yeah, no, I know what the question is. It's a
Yeah.
good question. From the contaminant perspective of high-res tools, the ministry doesn't accept high-res results to support ESA activities. It's a supplement, but they don't accept it. Similarly, you would think that HPT wouldn't be accepted. However, as I pointed out, that dissipation test, that's a slug test in itself. So you could theoretically package that to the ministry and get it approved. Has that been done yet? No.
No.
Have we communicated this to ministry? No. We're still building a strong enough case from a data point to hopefully present this to the ministry and say, hey, this might be the next jump that we experience, from grain size to slug test to pump test. Maybe the next one's HPT. So again, if you've got sites, we're hungry for data. We're hungry for proof of concept on it.
Okay. And then this is a very specific one, but what's the approximate MOB and DMOB to Montreal? And in fact, maybe say what is it to Toronto, or anyways, where does this equipment come from, and how much does it cost to send it out?
So we mobilized out of Kitchener, Ontario, which is about an hour west of Toronto for everybody. And then it would take us a day generally to get to the Montreal area. I don't have that number off the top of my head, but like basically a truck and one of our operators to drive out there, and then a drill rig to get out there as well. I don't know that number specifically off the top of my head, but I can sure get you an estimate if that's what you're looking for.
We've done work all over Canada with HPT.
We've taken HPT to Saskatchewan, Goose Bay, all over Ontario, BC. I can't think of anything in Manitoba specifically, but it's gone coast to coast. Like we go everywhere with this thing.
Okay. And I guess it's 2 o'clock now, so there are a few other questions, but if you do have any questions, feel free to reach out to Pat or Farouk. They had their QR codes up there. But you can also just email info@vei.ca. So I want to thank Pat and Farouk. Here you go. Round of applause.
Thank you, everyone.
And, actually, people have raised their hand. People have I think applauded in the chat there. And thank you to all the attendees for your time. And we will close it out. It is 2 o'clock now. Thank you, everyone. Have a good day.